Hello class, polynomial functions. A rectangular piece of cardboard has dimensions 2 feet by 5 feet. You want to form this into a box with no top by cutting equally sized squares from each corner and folding up the flaps. Use technology to find the size of the squares you should remove to maximize the volume of the resulting box. So we're going to begin our discussion on a thing called polynomials by first trying to solve this problem. So we have a 2 by 5 piece of cardboard, and we want to remove equally sized squares from each corner and then fold along the dotted lines, and that will lead to a shape that looks like this. The 2 is this length, and the 5 is the length all the way across the top. And the size of the squares, we're going to leave that variable. We're going to call this x by x. When we fold it into the box here, we're going to have a length, a width, and a height. And we want to express these three quantities in terms of x. For example, the height will be just x. The height is going to be that length right there after you fold the flap up. The L in my picture is the shorter of the two dimensions. So this is going to be the L of the box, and it's not 2 feet. This was 2 feet, but you removed 2 squares from the corners. It's going to be 2 feet, then remove x and remove x. In other words, it's going to be 2 minus 2x. When you fold up the flaps, the width of the box is going to be this length here. It's going to be 5 minus x minus x. 5 minus 2x again. The volume of a box is length times width times height. And I'm going to do the height first. The height is x. Then the length was 2 minus 2x. And the width is 5 minus 2x. So this becomes a volume function of x, where x is the size of the squares that you're removing from each corner. If x is really small, then you're going to have a very shallow box. Of course, x can only get so big because if there's a limit on how big of a square you can remove from each corner. If you're trying to remove a square from each corner of this box, but you only had 2 feet to begin with, then the largest possible square that you could remove without overlapping another square is 1 by 1. And so we have a restricted domain on this. We want x to be more than 0, but less than 1. If x is 0, it means you don't cut out any squares at all, hence you have no flaps and you have a volume of 0. And if x is 1, that means we've cut out too large of a square, and we're not going to have flaps to fold up. We're going to have a volume of 0 again. But now I'm going to just use technology to graph this function. Typed in right here, the second line is the blue function, and it makes this curve. I'm going to crop it next. Remember to use the curly brackets to crop it, and we want x to be between 0 and 1. So when you crop the graph, it's only showing you part of the entire graph. And the question is, what should x be? How large should the squares be so that the volume is maximized? Now in this image, the horizontal axis is x. The vertical axis is volume. So if you want to find the maximum possible volume, you got to just find this relative maximum here in our graph. And that point of data right there is 0.4402, 2.03. This is suggesting that if x is 0.44 feet approximately, then we will have maximized our volume, and that volume would be 2.03 cubic feet. Also notice that the graph to the naked eye looks like it's a parabola, but it's not a parabola because the symmetry isn't there. Notice that the vertex is not halfway between the x-intercepts. 0.44 and 2.03 is about there, and two x-intercepts at 0 and at 1. Remove squares that are 0.44 feet by 0.44 feet to get the max volume of 2.03 cubic feet. This situation is an interesting situation. It gives us a reason to want to study the class of functions that this volume function produced. The name of this kind of function is a polynomial function. We're going to experiment with technology by graphing various versions of the function below, where the parameters are any real numbers. We're going to type this into Desmos, and I typed in a times x minus r1, and it says, would you like to add a slider for these? And I'm going to say yes, add sliders for both. Currently we are seeing a graph of a curve, a times x minus r1, where a is 1 and r1 is 1. In other words, we're just seeing a graph of y equals x minus 1. Well, that's a line, slope 1, y-intercept negative 1. If you change a to different numbers, we get different slopes. Notice what is the same, though, as I let a vary, the x-intercept. R1 dictates where that x-intercept is. If I change R1 to 2, then we have an x-intercept at 2. Okay, now let's add another factor that looks like this and add a slider for R2. Now look what we're getting. As you vary R1 and R2 to different numbers and A to different numbers, you get a variety of different kinds of shapes. Notice all of them appear to be parabolic. When you have a number times x minus a number times x minus a number and FOIL it, you're going to get something of the form ax squared plus bx plus c, which is our family of functions called the quadratic functions, and they form the shapes that are known as parabolas. And notice that this is simply the factored form of our quadratic equations. A is going to be the leading coefficient. If A is positive, the parabola will open up. If A is positive and large, you get more and more narrow. If A is positive but close to 0, we get flatter and flatter. But if A is negative, then we have an upside down parabola and kind of flat. And as we go more and more negative, we get more and more narrow. But notice what's not changing as I toy with A, and that is where this parabola is crossing the x-axis. Let's go ahead and park A at 1. Let's drag R1 to 2, and then I will drag the second R2 around. We're getting parabolas that always have at least 2 as an x-intercept. And then the other x-intercept is going to be whatever R2 is. If both of the R's are both 2, notice that we have a phenomenon of the graph having an x-intercept at 2, 0, but not crossing the x-axis there. We say it touches the x-axis but does not cross it. But when the roots are different, we get 2 different x-intercepts, and the graph will cross the x-axis at both of the x-intercepts. Let's throw another one in here and add a slider for r sub 3. And now we're starting to get things that look a lot like what we saw with the volume function. If you were to FOIL this, you would wind up with an x cubed expression as the highest powered term. It's called a cubic polynomial. Let's leave a as 0.4. And as I drag the other r's around, as long as they're all different, notice I have 3 different x-intercepts, and the graph crosses at each x-intercept. If I make 2 of the r's the same and leave the other r something different, since 2 of the r's are the same, 0.4, that's still an x-intercept, but the graph now bounces off of the x-axis and does not cross it at 0.4, where it does cross at 3.4. If I make all 3 the same, 0.4 is the only x-intercept. That's because all the r's are 0.4. And notice that we cross through the x-axis at that location, although the graph does flatten out and then continues to cross through. If I were to throw another one on here, add a slider for r sub 4, now we start getting what are called 4th degree polynomials. If all the r's are different, let me change the y scales. There's 2 x-intercepts right here near -4. In fact, it's -4, -4.6. And then I have another x-intercept over here at 1. That's my r4. And then another x-intercept over here at 5.4. That's my r2. When all the r's are different, and there's 4 of them, you're going to see that the graph crosses the x-axis at the 4 different locations. If you can guess, if I make 2 of these r's the same, but the others keep different, notice what's going on this time. At the r's that are distinct, the graph crosses the x-axis. But at 5.4, we bounce off the x-axis. We touch it, but we don't cross it. Now, when 2 of the r's are the same, for example, the x minus 5.4 and another x minus 5.4, instead of writing them separately, you can just write x minus 5.4 and then put a square on those parentheses. We'll see that in a moment. Now, by hand, let's do the following. Here's a function that has a -2 as a coefficient in the front, and then an x minus 5, and then an x plus 3, and another x plus 3. I didn't have to put that square there. I could have put another x plus 3. But since they're the same, just combine them together and say x plus 3 squared. Now, we're going to expand this. This just means multiply it all out. And I'm going to do the square part first. Okay, so we have -2 times x minus 5. Go ahead and write down the x plus 3 twice, and then do the FOIL process here on the x plus 3. And then the next one, when I FOIL it, it's going to get x squared plus 3x plus 3x, so that's plus 6x, and then plus 9. All right, the next thing I'm going to recommend we do is FOIL next with the x minus 5. Distribute the first term across all 3, and then the second term across all 3. So there's actually 6 products that have to happen here. So that leaves, we have the -2 in the front, keep the parentheses. We do x times x squared, that's x cubed. X times 6x, that's 6x squared. X times 9 is 9x. Now I'm going to distribute the -5. -5x squared minus 30x minus 45. Then you look for any similar terms, like we have x squares and x squares, and x's and x's, those can be combined. So we have x cubed, 6x squared minus 5x squared is just x squared. 9x minus 30x is -21x, and then minus that 45. And then finally, we're going to distribute the -2. So we have -2x cubed minus 2x squared plus 42x, and then plus 90. This is said to be a polynomial in factored form, and then after we expand it, we're going to call this one the general or the expanded form. Notice I was careful to write in order of decreasing power. This is just convention. You put the x cubes, that's the largest, then the x squares, then the x's, and then the term that has no x's. This is called the constant term. We can see that there are a total of 4 terms, so we call this a 4-term polynomial. The highest powered term is called the leading term, and the highest exponent present, which is at 3, that's called the degree of the polynomial. So this is a 3rd degree polynomial. And then that negative 2 is called the leading coefficient. So the leading term is negative 2x cubed, but the leading coefficient is negative 2. Looking back at the original, if you were to try to find the x-intercepts here, set this equal to 0 and solve, you would say that if x is 5 or if x is negative 3, these are called the roots. And we're going to say that negative 3 is a root twice because of the square, because remember that square is just hiding the fact that we had an x plus 3 and then a second x plus 3. So we have a total of 3 roots. A root is simply an input value that leads to an output of 0. They're also called zeros. Now, the 3 roots are 5, negative 3, and negative 3. Now, some will say that you should say that there's only 2 roots here because one of them got repeated, and that's fine. You can say there's 2 distinct roots, but one of the roots occurs twice. And the word we're going to use here to describe this is multiplicity. So we're going to say the multiplicity is 2, and for the 5, multiplicity is 1. The multiplicity is just how many times the root is in your list. Now the graph of this function I went ahead and just put here. You can see that the roots, negative 3, show up as an x-intercept, and the other root is 5, shows up as an x-intercept. Because the multiplicity of 3 is even, it showed up twice in our list, which is obvious from the fact that there's a square on this x plus 3. And when you have an even multiplicity, you can expect the graph to hit the x-axis but not cross it. And notice it bounces off the x-axis not like a sharp V, but in a smooth, flat way, like a vertex of a parabola might. And then if the multiplicity of a real root is odd, it means that we're going to get a crossing at that x-intercept. A polynomial is a function with a general form as indicated in the given table. I did it by degree. So a degree 0 polynomial is anything of the form y equals a sub naught. The word naught I'm saying is naught. It means nothing, a sub 0. This is just a constant. This could be any real number. In fact, the coefficients can be any real numbers, although the leading coefficient should not be 0. A degree 0 polynomial is anything of the form y equals a number. So like y equals 5, it's called a 0-degree polynomial. Y equals 0 is a 0-degree polynomial. And all of these shapes, they make horizontal lines. Every horizontal line is considered a 0-degree polynomial. A first-degree polynomial has the general or expanded form of a1 times x plus a naught. And this looks just like the mx plus b structure. When you graph these things, you get a line, a non-horizontal line. So we'll call it a diagonal line. All diagonal lines are first-degree polynomials. If we include an x squared term, so we have a sub 2 x squared plus a sub 1 times x plus a naught, this is just the same thing as saying the general form for a quadratic, and they make parabolas. If I go even higher, there's also a x cubed term present. Then we have a third-degree polynomial. It has up to 4 terms, and these are called cubic, or third degree. And continuing, we have a fourth degree, and these are called quartic. You don't need to know this word, but... Now notice some things about general form. The coefficients could be any real number. These can be fractions, they could be pi, they could be square root of 2, they could be negative, they could be 0. So like maybe this term isn't visible because we would say a sub 3 is 0. The only restriction we want to really put is we don't want the leading one to be 0. Because if that's 0, then that term's gone, and this is no longer a fourth degree. It becomes a third degree. But notice the exponents. All the x's have exponents that are counting numbers, or whole numbers. You could make an argument that over here we have an x to the 0 present, because x to the 0 is the same thing as 1, and 1 times a naught is just a naught. This one has an x to the 1. So the exponents on x are whole numbers. So you're not going to see x to the 1/2, or x to the negative 7. That's going to be a key to helping us know when what we're looking at should be called a polynomial or not. Identify whether each function below is a polynomial. If so, put it in general form and give the leading term, degree, and constant. Okay, so look at the first one. We have a 3 over an x plus x to the 5th minus 7. Get the leading term first, so we're going to write the x to the 5th first. The 3 over x, though, that needs to be rewritten, and that's the same thing as plus 3 times x to the minus 1, and then we have the minus 7 over at the end. So it kind of looks like the structure of a polynomial, except with one problem. This is not a whole number. And the exponents are 0, 1, 2, etc. Remember, the natural numbers are 1, 2, 3, 4. The whole numbers are 0, 1, 2, 3, 4, etc. Because in this example here, we have an exponent on the x that's not a whole number, then this is not a polynomial. Let's move on to the next one. Here we have a radical 2 times an x. Now what's very important is to determine, is that radical, does it go over the x like this? It looks like it doesn't. The x is outside the radical. To avoid that potential confusion, let's put the x first. And now it's clear that the x is not inside the radical with the 2. I'm going to put the x to the 5th term first. I'm going to write that negative 2 over 3 as a negative 2/3 coefficient. So we have a negative 2/3 times an x to the 5th. It could be up here with a 2 or it can be next to the fraction like this, but don't put it down here with the x. That would be wrong. We don't have an x to the 4th, no x cubes, no x squares, but there is an x term. And then we have plus a 6. Okay, look at the exponents on the x's. The x has a 1 exponent on it, and the 6 is a constant. You could put the x to the 0 next to it if you want. You don't have to. But notice that there's a 0, a 1, and a 5 exponent on my x's. These are all whole numbers, so we are looking at a polynomial. Remember, the coefficients don't have these restrictions. You can have a fraction coefficient, you can have a radical coefficient, you can have any real number as the constant. So this is a polynomial. Put it in general form, we've already done that, and give the leading term, degree, and constant. Okay, so the leading term is the entire negative 2/3 x to the 5th. The degree is the 5. It's the highest power. I could have also said, what's the leading coefficient? I'm going to go ahead and put that in here anyway, even though I didn't ask for it. The leading coefficient is just the negative 2/3. And then lastly, the constant is the 6. If this had been subtraction right here, then you would have said the constant is negative 6. Okay, let's look at the h of x function. This time there's a 3 radical x. This time the radical is on the x. If you were to rewrite that in terms of a power, it'd be a 1/2 power. So right there is our issue. 1/2 is not whole. So this function is not a polynomial, and we're done. Okay, use technology to graph many different kinds of polynomials, then fill in the blanks of the statements below. Y equals ax to the 4th plus bx cubed plus cx squared plus dx plus e is not an acceptable parameter because e is going to be a problem. If you put an e here, it's going to assume that e is 2.7. Like if you go down here and just type in the letter e, notice what it says it is. E is a protected letter in Desmos. Okay, so here's a polynomial where if all of the coefficients are all 1s, we get this shape. Notice it has no x-intercepts. So not every polynomial has to have x-intercepts. I'm just going to hit play on these parameters and watch all the possible things that can happen. Let me change my vertical scale a little bit. As we're seeing a whole bunch of different 4th degree polynomials, I want you to notice a few things. Notice that the graphs are always smooth, no sharp corners. Further, notice that they're continuous. There's no breaks in the graph. The graph of a polynomial is always smooth, so no sharp corners. And the other word I would put here is continuous. So there's no asymptotes where there's a break in the graph, or there's no relocations and starting somewhere else, something like that. The 2 examples I just drew there have discontinuities, but polynomials are always continuous. Okay, now the next bullet. I'm going to park all of these at various values. I'm also going to reveal the graph that's just the leading term. At this window right here, the green graph and the purple graph are very different, but watch what happens when I zoom out. When you really zoom out, the two start to look similar. And when I talk about end behavior, I'm talking about what's happening on the very left end of our polynomial and on the very right end of our polynomial. And you can see that whatever the purple one is doing, the green one is doing too. It's only when you look at the very heart of the graph that you see that they're not the same function. But when you zoom out high enough, it looks like the 2 ends have the same behavior. So the answer to this one here, the end behaviors mimic the end behaviors of its leading term. Let's explore some very simple leading terms. And let's do a familiar function x squared. It's an even degree polynomial, and both ends go up. If I change that to a 4th degree, this is no longer considered a parabola. It still makes a cup shape though, and both ends still go up. If I do x to the 6th, both ends go up. X to the 8th, and both ends still go up, etc. Now let's explore some basic x to the odds, x to the 1. Notice the ends go opposite directions. The left side goes down and the right side goes up. Let's do x cubed. The left end points down and the right end goes up. X to the 5th. The left end points down and the right end points up. Let's go back to x squared. If I put a negative coefficient in front, so let's go ahead and put a back in front of there. When a is negative, our parabola opens down. That's also going to be true for a times x to the 4th. When a is positive, we have cup shapes that open up. When a is negative, we have cup shapes that open down. So if you have a negative leading coefficient and an even degree, you expect both ends to go down. But now what happens when you have an odd degree? A negative leading coefficient, like is what we have now. Left end is up, right end is down. And I say it starts high and it ends low. When you draw it left or right, starts high, ends low. That's always going to be true when you have an odd degree, but a negative leading coefficient. And a positive leading coefficient, odd degree, will start low and end high. So we're going to know a lot about the end behaviors of a polynomial by simply looking at its leading term. Now in all cases, the domain is all real numbers. Or you can say negative infinity to infinity. But the range, if you have a 3rd degree, this range would be all real numbers as well. In fact, all odd degree polynomials will have a range of all real numbers. But if this goes to an even degree, we have restrictions. Since all even degree polynomials, the ends point in the same direction, somewhere there has to be a max or a min, depending on which direction the ends go. Like in the case where both ends point up, there has to be a global minimum somewhere. And in the case where both ends point down, there has to be a global maximum somewhere. So we're going to say all real numbers if odd degree, and then we'll just say restricted if even degree. Finding the range can be difficult for the even degree cases. In fact, it's usually a topic of calculus. If a root is real and has an even multiplicity, okay, so let's go back to what we summarized up here. So we had 3 real roots. By real roots, I mean there's no imaginary numbers involved. Soon we're going to explore what happens when imaginary numbers are roots as well. But right now, all the polynomials that you're going to encounter, we just want to focus on the real roots. So 5 was a real root, and its multiplicity was odd because it showed up once in our list. And it's obvious that it's odd because the power on the x minus 5 was a 1. And then we know that the graph will cross the x-axis at that location. Okay, so we're actually doing the second bullet here. If a root is real and has an odd multiplicity, then at that root, the graph crosses the x-axis. If a root is a real number and it has an even multiplicity, then at that root, the graph touches but does not cross the x-axis. When in general form, remember general form is the expanded form, not factored form. When in general form, if all the powers of x are even, then the polynomial is symmetric about the. So here's a 4th degree polynomial. Okay, what happens if all of the exponents are even? So I'm going to zero out some of my coefficients so that I get rid of the odd powered terms. So I want to get rid of the x cubed. So I'm going to make b be 0. And then I want d to be 0 to get rid of the x part. Okay, now I want you to take a look at what kind of symmetry do you see on the resulting graph. And if I change the other values around, you should be noticing that all of these graphs, as long as all the odd power terms are gone, that all of these graphs have a symmetry, and that symmetry is across the y-axis. Okay, now let's explore when in general form if all the powers are odd. I have to zero out the a, the c, and the f. So we're actually going down to a 3rd degree polynomial. And so the only terms left here are the x cubed and the x. So all the powers are odd. And I'm going to let the b and the d vary and just see a variety of images here. Notice that all of these graphs do have a symmetry as well. The symmetry that we're seeing here is the symmetry about the origin, meaning that if you rotate the graph 180 degrees, either clockwise or counterclockwise, pivoting at the origin, then you will see the graph will become itself again. And this is the symmetry we say is symmetric about the origin. These are the same kinds of symmetries we talked about with even and odd functions. Okay, let's go on to the next slide. Find the polynomial function that is depicted below. Put it in general form. All right, the way to create the polynomial is to use our factored form. And by noticing whether we get crossing or bouncing off at the different x-intercepts. Then we have this extra point right here that we have to make sure we go through. Then we also have an x-intercept at 4, 0. We have another one at 2, 0. And then the last one looks like at -1, 0. So 3 x-intercepts. But what are their multiplicities? I see 3 distinct x-intercepts. Let's go in order, -1, 2, and 4. Well, because the graph is crossing, we know that the multiplicity has to be odd. Because the graph crosses at 2, also odd. But because we hit the x-axis but bounce off it, we know the multiplicity at this root is even. The easiest choices to make would be 1, 1, and 2. So now let's go straight to our factored form. And our function f of x equals, the factored form has an unknown coefficient a, and then I can start making these linear factors to construct this polynomial. If -1 is a root, then x minus that root will be a factor. So the r is the actual location of the root at -1. So change this r to -1, and this looks like x plus 1. If you set x plus 1 equal to 0 and solve, you get the root. You get -1. And then since the multiplicity we're going to say is 1, we just got to put a 1 there, which we don't need to write. Look at the next root. We cross at 2. So I need to do an x minus 2. That also crosses, so let's put a multiplicity of 1 on this one as well. And then the final x-intercept is at 4, so there's going to be an x minus 4, but we need this to have an even multiplicity. So there needs to be at least 2 of these, an even number. But we're going to just use an exponent instead, put a square there. And this is our polynomial with only one thing left to be determined in the a. Let's go ahead and actually type this in here and add a slider for a. And let's let a vary between -2 and 2. And you see we get all these different kinds of polynomials. But notice they all have something in common. They all cross at -1, cross at 2, but bounce off at 4. Now we have another point that we want our graph to go through, and that point is 1, 2. So now we just got to figure out what a is so that our polynomial goes through that point. somewhere around here. Maybe this isn't the exact answer we're looking for, but you get the idea. So with the technology, it looks like it's around negative 0.1 is what I need A to be. And the way to figure out A is to actually just plug in this point and solve for A. So we're going to change the output to 2. At the same time, I change the input to 1. So we have 1 plus 1 is 2. We have 1 minus 2 is negative 1. And we have 1 minus 4 is negative 3, but that one's squared. And we just have to solve for A. Do the squared first. That's a 9 times a negative 2. So we have a negative 18. So we have 2 equals A times negative 18. And then divide by negative 18, and we get A equals negative 2/18, which is negative 1/9. Now our instructions say here to put this in general form. For time's sake, I'm not going to do that. What that would mean is you would just have to multiply all this out. I will put my answer, and we put the negative 1/9 in front of that, and this is the polynomial that produces the shape that we see here. Let's verify it with the technology. So I'm just going to type in the fraction negative 1/9, and there it is. Let's move on to the next one. Do the following for the given polynomial function. Find the roots and their multiplicities, find the y-intercept, determine the end behaviors, determine whether there is even or odd symmetry, and graph by hand and confirm with technology. So we have to do some factoring here. Notice there's no constant term, which means there's some x's that could be factored out. I usually pull out the negative, look for any common numbers in the coefficients that could be factored out. Looks like the best I can do here is to factor out a negative 1 times an x times and then an x squared minus 4. Sometimes people don't bother putting the parentheses on that. They just say factor out negative x. That's fine. But I like to think of it as a leading coefficient and then some factors involving x's. Now we're not done factoring here because x squared minus 4 is a difference of squares. So that continues to factor, and it looks like this. Now you could put a phantom minus 0 here because all of these structures are x minus a number, x minus a number, x minus a number. So your roots are whatever number is being subtracted from x. So 0 is a root, 2 is a root, and then this one's going to be negative 2 is a root. Because you want to think of the plus here as really subtracting a negative 2. You don't have to do that kind of stuff. And in fact, you could even leave those parentheses off. But when you set the polynomial equal to 0 and solve, this is a product of 3 things. The leading coefficient doesn't matter. It just matters what x's you would pick to make those factors equal to 0. We get 0 as a root, we get 2 as a root, and we get negative 2 as a root. Next thing is look to the exponents. This is x to the 1. There's a 1 here and there's 1 there. So these all have multiplicity 1. 1 is an odd number, which means that the graph is going to cross the x-axis at these 3 locations. Find the y-intercept. The y-intercept is always found by plugging 0 in for x. We just get 0 back, which we already knew. If 0 is an x-intercept, then it's also going to be the y-intercept. 0, 0 is a point on our graph. It's an x-intercept and the y-intercept. 2, 0 and negative 2, 0. The end behaviors is you just have to know what the graph of negative x cubed looks like. Well, x cubed looks like this. Negative x cubed is its mirror image. So you focus on just the leading term to get the end behaviors. So we know that this graph is going to start high and end low. We'll be up here in the second quadrant, and then we're going to finish going down into the fourth quadrant. And then whether there's even or odd symmetry, now we look at the general forms. Don't look at the factored form for doing symmetry. Look at the general form up here, and look at the powers. There's a 1 and a 3. These are the only powers on x. They're all odd. So this tells us that there's going to be a symmetry about the origin. That means that whatever I wind up drawing on this half of the graph, I should be able to rotate that 180 degrees and make it match on this half of the graph. Okay, so here we go. So we knew that it started high, so we started up here in the second quadrant, and now I'm imagining the graph going this way, right? We're going to hit the x-intercept at negative 2. We're going to cross because of the odd multiplicity. It's going to have to turn around smoothly and get to 0. It's going to have to cross at 0, and then I'm going to have to do an identical bump there and then finish low. So here's what our graph is going to look like. Now let's go ahead and graph this just to confirm. And sure enough, we have this basic shape. Now one thing you don't need to be worried about when graphing by hand, and that's how far down should I make this bump go and how far up should this bump go. The only thing I know for sure is that there needs to be the odd symmetry. It's more a calculus topic to determine how far down and how far up these relative maximums and minimums are. If you want to get a little more precise by hand, you're just going to have to plot more points. But right now we're just trying to capture the basic flow of the polynomial. Let's move to the next one. Similar, so this is presented in general form. We've got to do some factoring. Notice, again, there's no constant term here, so that means I can factor out x's. Also, all of these coefficients are even, so I could take a 2 and an x out. 2 is the leading coefficient in x factors. That leaves x squared plus 6x plus 9. Then we try to factor this trinomial. We need to hopefully break this down into 2 binomials. By the way, a single term polynomial is called a monomial. A double term polynomial is called a binomial. 3-term polynomial is called a trinomial, and then after that we just say it's a 4-term polynomial, a 5-term polynomial, etc. So we started with a trinomial here. We did some factoring. There's a monomial there, but here's still a trinomial there, and we're going to factor that trinomial. We need two numbers that multiply to 9, add to 6. That's going to be positive 3 and positive 3. Notice that they're identical, so I recommend you use the power notation. So you got to write x plus 3 squared. Now when I set this equal to 0 and solve, I'm going to get 0 from this x and negative 3 from this x plus 3. But then you look to the exponents. On the x there's a 1, but on the x plus 3 there's a 2. So this one here we say the multiplicity is 2, but the multiplicity of 0 is 1. Next, find the y-intercept, plug 0 in for x. Again, 0 is an x-intercept, so 0 is also the y-intercept. Determine the end behaviors, so 2x cubed. 2x cubed is x cubed, but stretched vertically, so there's no reflection, so it starts low, ends high. 0 is an intercept, and so is negative 3. Determine whether there's even or odd symmetry. Look to the exponents. There's a 3, a 2, and a 1. And these are not all even nor not all odd. So we have a mixture of even and odd. When this happens, no symmetry about the y-axis and no symmetry about the origin. Okay, now let's go ahead and do our graph. So we start low and we get to this intercept. Well, the question is, what happens at intercept? Do we cross or not cross? And so we look to the minus 3. It came from this factor right here, and the multiplicity is 2. That means we touch but don't cross. So I'm going to change this and make it bounce off smoothly. Now this is continuous, so it's going to have to turn around and get to that intercept eventually. And then at this intercept it has to cross, because the multiplicity of 0 is 1 and 1 is odd. So it's going to cross and then end high. I'll leave it to you to confirm with technology that your basic shape is something like that. Same instructions, but new polynomial. This is a trinomial. There's no common factors in the coefficients, and we do have a constant term of 4. So I can't factor out any x's, so I just have to try to factor this trinomial into two binomials. Split the x to the 4th up, that's x squared and x squared. Now two numbers that multiply to 4 but add to negative 4. The negative 2 and negative 2 should do it. And just FOIL this to make sure it works, right? X to the 4th minus 2x squared plus 4 works out. Now each of these is a difference of squares. I trust if this was a 9 instead of a 2, you would quickly go to x minus 3 times x plus 3. Well, it doesn't matter whether or not this number here is a perfect square or not. You can still factor. We have x minus rad 2 times x plus rad 2. And then the other one factors the same way. But notice they come in pairs now. So we have x minus rad 2, that happens twice, so that's squared. And x plus rad 2 occurs twice, so we'll put a square on that. So when I set this equal to 0 and solve, I get only two distinct answers. Our roots are radical 2 and negative radical 2. Then we look to the exponents on their factors to see what the multiplicities are. Right, there's a 2 there and a 2 there. The y-intercept next. N is our function, plug 0 in, I get 4. You always get the constant when you do the y-intercept. We need to do the end behaviors. The leading term is just x to the 4th, and that looks like a flattened cup shape, but both ends up. So this one starts high, ends high. Determine whether we have even or odd symmetry. Notice all the powers are even. You could put an x to the 0 here on the constant term, but all the exponents, when in general form, all even. When that happens, that tells us that we have symmetry about the y-axis. All right, ready to graph this thing. I'm going to do different scales. Each block is 1 horizontally, but vertically each block is 2. So this would be 2, 4, 6, etc. So 0, 4 is our y-intercept. I'll put that right there. Horizontally, we'll do a different scale. Let's make that negative 2 and positive 2, negative 1 and positive 1, etc. Radical 2 is approximately 1.4. So we have an x-intercept at a negative radical 2 and positive radical 2. Those are the x-intercepts. And the graph starts high. Now, at this x-intercept, do we cross or bounce off? The multiplicity is even, so we're going to bounce off the x-axis. And we're going to bounce off on this one as well. So that tells me that our shape is going to make like a cup shape when it hits there. Then it's going to come up to here, hit there, and then do a mirror image. So this means don't go over and then turn around, because then you won't have symmetry about the y-axis. Both ends point up. We hit the x-axis twice, but it never crosses the x-axis, and we have a y-intercept of 0, 4, and we have symmetry across the y-axis.